In the autumn of 1943, the air war over Western Europe had reached a new phase. The United States Army Air Force's heavy bombers plunged deep into German-occupied territory, often escorted by American fighters such as the P-47. The Luftwaffe's doctrine was built on short, sharp engagements. Fire a cannon burst, force the enemy into a low-altitude fight, exploit superior maneuverability, and finish him off. German pilots were trained and drilled on these assumptions, and their equipment, including the 20mm wing-mounted cannon, was optimized for it. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. In contrast, American fighter design followed a different path. The Thunderbolt was built around one idea: mass, power, and survival. Its engineers accepted a heavy airframe, a massive engine, and 8 heavy machine guns, even though that went against the nimble dogfight ideal. The German high command believed they held the edge: faster rate of climb, tighter turning fighters, and cannon bursts that would shred enemy formations. The American belief was simpler: build more, build tough, and shoot more bullets in more places for longer. On paper, the 20mm shell had greater destructive potential per round, yet the disparity between ideology and operational reality was widening. American armorers loaded each Thunderbolt with 3,200 rounds of .50 caliber ammunition, more than any other Allied single-engine fighter. The sheer volume of fire created by 8 guns firing simultaneously meant the chance of strikes through fragile aircraft skin became very high. Meanwhile, German assessments of the 20mm cannon spoke to fewer rounds carried, heavy recoil, slower rate of fire and less ammunition on board, reliable in ambush but less so in attritional engagements. Yet despite that, the Luftwaffe kept faith with its cannon-armed fighters. Their early successes and legacy of dogfight mastery made change slow. They assumed the next Allied fighter would be like the last one: light, maneuverable, fragile. What the Americans brought instead was a flying fortress in fighters' clothing. By the spring of 1944, German pilots began reporting something odd. The P-47 seconds they encountered often absorbed hits that would have spelled the end for a Bf-109 or FW-190. Battle damage reports noted engine cowlings punched through, control surfaces mangled, fuel lines pierced, yet the P-47 climbed out, turned away or returned to base intact. German ground crews at captured aircraft centers raised eyebrows. What were they missing? What did this beast have that so many of their carefully aimed 20mm cannons could not deliver? And so begins our deeper dive into the specifics. The unit crews, the ammunition types, the industrial numbers, the physical reality of hundreds of rounds meeting thick American armor. In the next section, we will dissect the weapon systems and the psychology of the pilots, how expectation led to surprise, how doctrine collided with mass production, and how the Germans found themselves rethinking what they believed a fighter really should be. The morning of September 20th, 1943, dawned over northern France with a deceptive calm. The sky, a muted canvas of steel and slate, hung low, promising both concealment and peril. On the tarmac, at an isolated Luftwaffe recovery airfield near Rechlin, a peculiar sense of anticipation gripped the engineers and test pilots assigned to the newly arrived P-47 Thunderbolt. The aircraft had been recovered almost intact from the fields near Rouen, having survived a strafing run that left the landing gear collapsed but the engine and airframe largely undamaged. For the German pilots and engineers who approached it, this was more than a captured plane. It was a mechanical enigma, a manifestation of Allied industrial philosophy that had already begun to unsettle their understanding of aerial warfare. The Thunderbolt's reputation had preceded it. Luftwaffe pilots had encountered these massive fighters over the skies of occupied France since April of that year, escorting bombers on deep raids into German-held territory. Initial combat reports had been a mixture of incredulity and frustration. The P-47 was enormous compared to the nimble Messerschmitt Bf-109 and the Focke-Wulf FW-190, yet it exhibited resilience that German pilots could scarcely comprehend. Machine gun fire, even cannon shells, that would have destroyed a Bf-109 left, thunderbolts limping home, wings scorched, control surfaces torn, engines streaming oil, yet still operational. These accounts filtered back to engineering staffs at Rechlin and other Luftwaffe testing facilities, forming a growing dossier that was as mystifying as it was alarming. Hans Werner Lehr, the principal test pilot and a decorated veteran of over 100 combat missions on the Eastern Front, approached the P-47 with cautious curiosity. Lehr had flown every operational German fighter from early Bf-109 models to the latest FW-190A8 variants, giving him an encyclopedic understanding of handling characteristics and engine performance. He had developed a professional skepticism toward captured aircraft, knowing full well that the Luftwaffe's intelligence units occasionally exaggerated their capabilities to mask failures in doctrine or tactics. Yet this Thunderbolt presented a dilemma. It was not merely another captured plane, it was a puzzle whose components and systems challenged every assumption German engineers had held about fighter design. The first impression upon walking around the aircraft was its sheer mass. The P-47D variant, recovered, measured nearly 10,000 pounds empty, almost double the weight of a Bf-109G. Lehr could feel the difference beneath his gloved hands, the thickness of the fuselage metal, the reinforced panels protecting the engine and cockpit. Every panel bore signs of precision construction, rivets uniformly spaced, access hatches carefully engineered for maintenance. The radial Pratt & Whitney R2800 double Wasp engine alone represented an engineering philosophy alien to Germany. Raw displacement and mechanical reliability prioritized over minimal weight and agility. Lehr spent the better part of the morning on the ground, systematically documenting each instrument and control. The cockpit presented an array of levers, dials, and gauges that, in combination, constituted a complex network of automated systems unknown in contemporary Luftwaffe designs. German fighters relied heavily on pilot input for mixture, throttle, and propeller pitch adjustments. The Thunderbolt offloaded much of this to mechanical and aerodynamic automation, reducing the cognitive load on the pilot in combat, but requiring greater engineering sophistication. The turbo supercharger system alone demanded precise understanding of exhaust flows, manifold pressures, and air density variations at high altitude. For German engineers, many of whom had only theoretical knowledge of such systems, the P-47 was an unprecedented exercise in applied industrial physics. By midday, Lehr initiated the engine start sequence, methodically following the procedure detailed in the minimal documentation recovered with the aircraft. The radial engine roared to life with a deep, resonant vibration that rattled the metal stands and caused several nearby technicians to instinctively step back. The sound was fundamentally different from the high-pitched bark of German inline engines, its power immediately perceptible through both audio and tactile feedback. Lehr noted the torque and responsiveness of the controls, the immediate effect of propeller pitch adjustments, and the subtle responsiveness of the hydraulic systems that managed the landing gear and flaps. Each movement, each lever, confirmed that this was a machine designed with redundancy, survivability, and sustained high performance in mind. The afternoon was dedicated to comparative analysis. Lehr directed several technicians to measure armor plating thickness, engine displacement, and control cable routing. The armor was substantial: a 1/4-inch steel backplate for the pilot's seat, bulletproof glass on the forward canopy, and protective panels for critical engine components. Fuel tanks incorporated a self-sealing design using multiple layers of treated rubber. German engineers, accustomed to prioritizing speed and maneuverability, found this approach counterintuitive. It violated the prevailing doctrine that agility, rather than endurance, determined survival. Yet the empirical evidence could not be ignored. P-47 seconds returned from missions battered, punctured by multiple cannon shells, yet remained controllable and operational. The following morning, Lehr took the Thunderbolt on its first test flight. The takeoff roll was unusually long due to the aircraft's weight, but the radial engine delivered immediate and sustained thrust once airborne. Lehr ascended to 15,000 feet, a conservative altitude for initial evaluation, and began testing maneuverability, climb rate, and throttle response. The aircraft handled differently than any German design, sluggish in tight turns but extraordinarily stable in dives. Its enormous kinetic energy allowed it to sustain speed through maneuvers that would bleed off energy in lighter fighters. Most striking to Lear was the weapon system. The 8.50 caliber Browning machine guns provided a concentrated and devastating volume of fire, far exceeding the nominal output of standard German fighters. In a controlled strafing simulation, the gun's recoil was manageable, the accuracy impressive, and the rate of fire sustained without noticeable degradation. Over the next several weeks, Lear and his team subjected the P-47 to exhaustive testing. German ammunition and training rounds were fired into the fuselage, wings, and control surfaces to simulate combat damage. Each round's impact was carefully documented. Damage that would have rendered a Bf-109 inoperable merely scratched the Thunderbolt. Bullets penetrated outer panels, shredded skin on the wings, and even punctured fuel lines, yet the aircraft remained fully controllable. The redundancy engineered into control systems meant that a single hit could not compromise a critical flight function. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. These tests created a psychological revelation among the engineers. The Luftwaffe had long relied on assumptions of technological superiority in firepower and precision. Reports from the Eastern and Western fronts had reinforced the belief that a skilled pilot and a nimble aircraft could always dominate a heavier, slower opponent. The Thunderbolt shattered that assumption. 8 concentrated machine guns, each firing at rates exceeding German designs, combined with armor and mechanical redundancy, produced a fighter that could absorb punishment while simultaneously delivering far more lethal output. German aces who observed these tests, including pilots with hundreds of confirmed kills, could scarcely reconcile the performance with the doctrines ingrained through years of combat. Meanwhile, intelligence officers meticulously catalogued every feature of the aircraft. The Pratt & Whitney R2800 engine was dissected to reveal material choices, cylinder tolerances, and cooling system design. Engineers traced the turbocharger ducting through the fuselage, noting the attention to heat management and pressure regulation. Every bolt and rivet was measured, every hydraulic line and cable routed with redundancy in mind. The team discovered that American engineers had deliberately distributed loads, separating critical systems so that a single hit could not compromise multiple functions. The Germans recognized this as a philosophy fundamentally different from their own, where efficiency and weight minimization were often prioritized at the expense of survivability. The psychological impact on Luftwaffe pilots grew with each successive evaluation flight. Veterans who had expected the Thunderbolt to be a fragile adversary now faced a harsh reality. The American fighter was effectively a flying fortress. They marveled at how a plane twice the weight of a Bf-109 could accelerate out of a dive, sustain multiple hits, and return home without catastrophic failure. Pilots began recounting stories of engagements where they emptied 20mm cannon magazines into Thunderbolts, only to watch the aircraft shrug off damage that would have immediately disabled German designs. Lear himself kept a meticulous log of these observations, noting the divergence between theory and empirical performance. These insights directly influenced Luftwaffe tactical planning. Units were instructed to avoid conventional turning dogfights with Thunderbolts, recognizing that their nimble fighters could not exploit weaknesses that did not exist. Instead, tactics shifted to ambushes during takeoff, low-altitude attacks, or coordinated assaults in which multiple aircraft attempted to overwhelm the Thunderbolt simultaneously. Yet even these approaches were only partially effective. Test data demonstrated that while P-47 seconds were slower to turn, they could absorb initial attacks and counterattack with devastating firepower. The aircraft's design philosophy, survivability over agility, redundancy over simplicity, consistently neutralized the advantages of the lighter, more maneuverable German fighters. By late October, the captured Thunderbolt had undergone over a dozen simulated combat scenarios, each meticulously recorded. Lear and the engineering team compiled performance charts, documenting rates of climb, dive speeds, structural resilience, and weapon effectiveness. These data were shared with higher command, influencing aircraft design considerations for new Luftwaffe models. Yet there was an underlying despair. The Germans recognized that they could understand the engineering principles behind the P-47, but replication was virtually impossible under the constraints of wartime industry. Material scarcity, production bottlenecks, and the relentless pace of Allied bombing campaigns made the construction of equivalently robust aircraft unfeasible. The captured Thunderbolt had, in essence, become a teacher. It demonstrated the profound difference between doctrinal expectation and technological reality. German engineers acknowledged, often in private notes, that the American approach prioritized a different hierarchy of values: survivability, sustained firepower, and industrial mass production, rather than minimum weight and individual pilot skill. The psychological shift extended beyond engineering. It seeped into pilot perception, altering the way Luftwaffe aviators approached engagements. Where once a single pilot's maneuver could decide an encounter, the Thunderbolt demanded coordinated action, careful planning, and a grudging respect for the enemy's technological advantages. By mid-November, the Rechlin facility had completed the formal evaluation. The P-47 was debriefed in exhaustive reports, detailing every system, every metric of performance, every observed anomaly. Lear summarized his findings in a candid memorandum. The Thunderbolt's design represents a paradigm in which the survival of the aircraft and pilot is prioritized above the limitations of individual engagement. It is robust, redundant, and immensely powerful. Any tactical assumptions based on comparative agility are rendered obsolete when facing this machine. Combat effectiveness derives from sustained firepower and the ability to absorb punishment beyond conventional expectations. This memorandum, distributed among senior Luftwaffe command, underscored a subtle yet crucial irony. Germany had mastered the art of precision, speed, and tactical skill, yet the Americans had mastered resilience, redundancy, and industrial scale. The Thunderbolt embodied an approach that leveraged material abundance to offset individual vulnerability, creating an aircraft that could withstand the very tactics designed to destroy it. Pilots and engineers alike grappled with the implications. The lessons were clear, yet painfully unapplicable. Germany could study the aircraft in minute detail, but replicating its philosophy required resources that no longer existed in sufficient measure. The captured P-47 continued to fly under German control throughout late 1943, serving both as a practical evaluation platform and a psychological reminder. Each test sortie, each measured dive, each target engagement reinforced the central truth. Allied industrial philosophy and engineering choices were as decisive as tactics and skill. For Luftwaffe pilots, the 8.50 caliber machine guns of the Thunderbolt were more than mere armament. They were symbols of an approach to warfare that the Germans could admire, fear, and never fully counter. The psychological shift, subtle but profound, echoed throughout the ranks. Veterans spoke of a mixture of awe and frustration. Tactical manuals were reconsidered. New pilots were cautioned about engagements that previously would have been routine. The lessons extended beyond the immediate theatre of air combat. Engineers who had studied the Thunderbolt applied the insights wherever possible, influencing designs of late-war German prototypes such as the FW190D9 and attempts at reinforced versions of the Bf109, yet the fundamental limitation remained. Resource constraints prevented widespread adoption of the resilience-based design philosophy exemplified by the P-47. In essence, the captured Thunderbolt had revealed a gap between theoretical knowledge and practical capability, highlighting the limits imposed by material scarcity and industrial capacity. The enduring legacy of the captured Thunderbolt at Rechlin was not a single tactical innovation, nor a dramatic shift in air superiority, but rather a transformation in understanding. German engineers and pilots came to recognize that the American approach to fighter design integrated three critical elements: survivability, redundancy, and overwhelming firepower. These elements, combined with industrial scale, produced a class of aircraft that could endure what had previously been considered fatal damage, maintain combat effectiveness, and impose strategic challenges that could not be mitigated solely through pilot skill or tactical ingenuity. As the first frost of November settled over northern Germany, the Thunderbolt stood silently on the tarmac, a testament to engineering ambition and industrial philosophy. Its presence had reshaped the expectations of German aviators, challenged long-held assumptions about air combat, and underscored a sobering truth. Material abundance, methodical engineering, and systematic redundancy could outmatch agility, skill, and even courage. For those who had witnessed the tests firsthand, the lesson was indelible. The P-47 Thunderbolt had not only survived the skies over France, but had survived the judgment of its adversaries, exposing both the limitations and the vulnerabilities of an air force already stretched to its limits. The story of these evaluation flights, meticulously documented and preserved in Recklin's archives, became a cornerstone of Luftwaffe introspection. It was studied, debated, and occasionally cited in design reviews, though the structural and material limitations of the German war economy rendered many of the insights aspirational rather than actionable. The Thunderbolt, in its quiet resilience and brutal effectiveness, had achieved an ironic immortality. It taught lessons that could be understood but not fully applied, symbolizing the growing disparity between Allied material capacity and German resource constraints. As the final test flights of December 1943 concluded, Lear reflected in his logbook, "This aircraft is more than a machine. It is a manifesto. It embodies an industrial philosophy that transcends tactical calculation, redefining the parameters of what a fighter can endure and accomplish. Our doctrines, however sound in theory, confront the stark reality of what can be achieved when engineering is unrestrained by scarcity, guided by foresight, and executed with precision. To defeat such a design is to confront the limitations not of pilots, but of an entire system of production and resource allocation." The winter of 1943 deepened over northern Germany, bringing with it short days, long nights, and a biting frost that crept across the tarmac at Rechlin. The captured P-47 Thunderbolt had become a fixture at the evaluation facility, its presence a constant reminder of an industrial and tactical reality that Luftwaffe pilots and engineers could neither ignore nor fully counter. In the dim light of early December mornings, technicians scurried about the airfield, performing routine maintenance and preparing data for analysis, while pilots like Hans-Werner Lehr prepared for another series of test flights designed to simulate operational conditions. Each sortie was undertaken with meticulous precision, a combination of technical curiosity and cautious respect for the aircraft's capabilities. The initial fascination with the Thunderbolt had evolved into a broader understanding of its implications. The aircraft represented not merely a captured opponent but a philosophical divergence between the industrial approaches of the United States and Germany. While German aircraft design emphasized speed, maneuverability, and pilot skill, the American approach integrated robustness, redundancy, and sustained firepower, delivered at scale through a well-resourced industrial infrastructure. This divergence forced Luftwaffe engineers to confront the uncomfortable truth that technological excellence, when divorced from material abundance, could be rendered insufficient in the face of an opponent with both industrial capacity and pragmatic design philosophy. By late December, the captured P-47 had undergone every feasible evaluation, from low-altitude gunnery simulations to high-altitude dives and structural stress tests. German engineers meticulously catalogued every feature, noting the thickness of armor, the layout of control systems, and the resilience of the airframe to repeated impact. Each observation reinforced a central theme. Survivability was as crucial as maneuverability, and redundancy within mechanical systems could turn the tide of combat more decisively than pilot skill alone. Reports highlighted the aircraft's self-sealing fuel tanks, multiple independent fuel pumps, distributed control cables, and backup electrical circuits. Even when exposed to simulated battlefield damage, the P-47 continued to operate with remarkable reliability. These insights began to reshape Luftwaffe training manuals, albeit cautiously. Pilots were briefed on the limitations of conventional engagement strategies when facing Thunderbolts, particularly the hazards of low-altitude dogfights and head-on confrontations. Tactical directives emphasized coordinated attacks, simultaneous strikes, and the exploitation of terrain or weather conditions to offset the American fighters' advantages. Yet, even as theory adapted, reality remained daunting. Pilots who had previously relied on agility and precision now confronted a machine whose resilience could nullify their most practiced maneuvers. Many veterans noted a psychological strain. Understanding the Thunderbolt's capabilities did not make them less formidable in the sky, but it introduced a persistent awareness of vulnerability that had previously been abstract. By early January 1944, Rechlin had become a hub for the systematic study of captured Allied aircraft. The P-47, while not unique in being examined, stood out for the intensity of scrutiny it commanded. Engineers, pilots, and intelligence officers rotated through daily evaluations, each contributing to a growing repository of knowledge. Among these personnel, there emerged a subtle but pervasive consensus. The Thunderbolt embodied an approach to warfare that leveraged industrial and material advantages to maximum effect, creating a fighter whose operational endurance challenged German doctrine. The aircraft's design philosophy was not merely technical, it was ideological, representing a commitment to sustained combat effectiveness that transcended individual skill or battlefield circumstance. The aircraft's offensive capabilities, particularly its 850 caliber machine guns, remained a focal point of study. Simulated engagements revealed that the Thunderbolt could deliver concentrated fire over prolonged periods without overheating or structural compromise. German ammunition, calibrated for conventional targets, often failed to penetrate critical systems, underscoring the discrepancy between design, intent, and operational expectation. Engineers observed that the placement and redundancy of weapon mounts allowed for continued fire even when individual guns were damaged. In effect, the Thunderbolt could absorb damage, continue its mission, and retaliate with lethal force, a combination that challenged both tactical assumptions and morale. The impact on Luftwaffe pilots was profound. Pilots who had previously equated superior maneuverability with battlefield dominance now faced an adversary whose strength lay in resilience and firepower. Anecdotal reports from Eastern and Western Front operations, corroborated by Rechlin evaluations, indicated that engagements with P-47 seconds often resulted in disproportionately high German losses relative to damage inflicted. The psychological effect was subtle but cumulative. Repeated encounters with Thunderbolts fostered a grudging respect, tempered by frustration at the limitations imposed by existing doctrine and material constraints. Veterans wrote of a shift in perception, recognizing that the skill of the pilot, while essential, could not fully compensate for disparities in design, philosophy, and industrial support. The captured Thunderbolt's influence extended beyond immediate tactical considerations. Engineers began exploring adaptations of redundancy and survivability principles within new German designs. Late-war prototypes, including reinforced variants of the Bf-109 and experimental Fw-190 models, incorporated thicker armor, dual control circuits, and improved fuel tank designs. Yet these modifications were constrained by material shortages and production bottlenecks, highlighting the practical limits of emulating American industrial philosophy under the pressures of total war. In essence, the Thunderbolt had become a benchmark for what could be achieved when engineering priorities aligned with abundant resources, a standard the Luftwaffe could study, but never fully realize. By February 1944, Rechlin's evaluation flights had become more structured, simulating operational sorties rather than purely experimental maneuvers. Lear and other experienced pilots conducted mock intercepts, strafing runs, and dive recoveries, documenting aircraft behavior under stress conditions. These exercises confirmed earlier findings. The Thunderbolt's large mass, while reducing agility, conferred stability and energy retention that German fighters could not match in sustained engagements. Pilots noted the aircraft's ability to maintain speed through turns, its resistance to structural deformation, and the consistent performance of its propulsion system under varying altitudes and temperatures. Each flight reinforced the emerging narrative that survivability and redundancy, when combined with concentrated firepower, constituted a decisive strategic advantage. As these evaluations proceeded, the Luftwaffe faced the broader operational reality of Allied air dominance. Production figures revealed the scale of American manufacturing. Thousands of P-47 seconds and P-51 Mustangs were being delivered monthly, with uniform quality and reliability. By contrast, German productions struggled under the constraints of strategic bombing, resource scarcity, and logistical disruption. The captured Thunderbolt thus served as both a technical lesson and a symbol of industrial disparity. Engineers recognized that understanding American design could not compensate for the inability to produce equivalent aircraft in sufficient numbers. Tactical adaptation, while necessary, could not overcome the structural advantage conferred by sheer industrial capacity. In March 1944, a significant event crystallized the lessons learned. A squadron of Bf-109G fighters, tasked with intercepting a formation of P-47 seconds escorting bombers over northern France, reported unusually high losses despite favorable weather and initial tactical positioning. Post-mission analysis, incorporating Rechlin data, highlighted several factors. The Thunderbolt's durability allowed them to absorb initial strafing attacks, their firepower inflicted disproportionate casualties, and their ability to maintain formation integrity under duress prevented effective German exploitation of weak points. Pilots who survived the engagement documented a mixture of astonishment and frustration, noting that conventional engagement strategies were insufficient against an aircraft designed to withstand and retaliate under fire. The psychological impact of these operational encounters reinforced the conclusions drawn at Rechlin. Commanders and pilots increasingly accepted that American industrial philosophy had created an aerial platform capable of reshaping the dynamics of air combat. The Thunderbolt's resilience, coupled with the Americans' ability to produce it en masse, introduced a form of attritional advantage previously unaccounted for in German doctrine. Even the most experienced Luftwaffe aces acknowledged that technical skill alone could not overcome the combined effect of durability, concentrated firepower, and sustained production. The captured Thunderbolt also informed the Luftwaffe's strategic planning. Intelligence officers synthesized Rechlin findings into operational guidelines, advising units on engagement, distance, attack angles, and coordination requirements. Pilots were trained to exploit environmental factors, such as cloud cover and sun positioning, to mitigate the Thunderbolt's advantages. Yet the limitations imposed by material scarcity persisted. Germany could not manufacture aircraft with comparable redundancy or armor, and the pace of attritional losses eroded the effectiveness of even highly skilled pilots. The Thunderbolt thus became a touchstone for the broader disparity between strategic aspiration and operational reality. By April 1944, the accumulated data had produced a comprehensive technical dossier on the P-47. It included detailed schematics of the engine, control systems, hydraulic circuits, and armament distribution. Engineers annotated material properties, tolerances, and redundancy measures. Test pilots contributed experiential notes on handling, energy retention, dive recovery, and weapon effectiveness. This document became a reference not only for tactical adaptation, but also for conceptual discussion within Luftwaffe circles regarding aircraft philosophy. Yet, the underlying truth remained immutable. While knowledge could be transferred, the capacity to implement equivalent designs was constrained by industrial and material realities. The captured Thunderbolt's presence continued to influence pilot psychology. Veterans reported a persistent awareness of vulnerability when engaging Allied aircraft, even when operational circumstances favored the Luftwaffe. Training emphasized the necessity of tactical innovation and coordination, yet pilots often reflected privately on the frustration of confronting a platform that could endure damage they had been trained to exploit. This subtle psychological shift, an acceptance of limits imposed by the enemy's industrial and engineering advantages, permeated the Air Force, influencing both decision-making and risk assessment. Throughout the spring of 1944, Rechlin continued to facilitate test flights and technical analysis. Engineers examined incremental failures, subjected the aircraft to extreme stress tests, and monitored systems under repeated strain. Each test reinforced the conclusion that the P-47's survivability was intentional, a deliberate design philosophy rather than an incidental consequence of size or material choice. Pilots participated in simulations designed to test both offensive and defensive capabilities, confirming that conventional German tactics required substantial adaptation. The cumulative effect was a growing appreciation for the interplay between engineering, foresight, and operational effectiveness. As the Allies prepared for the invasion of Normandy in June 1944, the lessons of the captured Thunderbolt assumed strategic significance. Pilots and commanders who had trained with and studied the aircraft understood that engagements with American fighters would involve confronting machines optimized for resilience, firepower, and operational endurance. The tactical manuals derived from Rechlin evaluations emphasized caution, coordination, and avoidance of predictable engagement patterns. While these adjustments could not negate the broader strategic advantages enjoyed by the Allies, they represented the Luftwaffe's most informed attempt to mitigate the challenges posed by a platform whose design philosophy outpaced their own industrial capacity. The captured P-47 remained at Rechlin into the summer of 1944, continuing to serve as both a testbed and a symbol. Engineers refined their understanding of American construction methods, material selection, and design redundancy. Pilots internalized the lessons of survivability and firepower, translating them into tactical awareness. Intelligence officers catalogued every insight, producing reports that informed training programs and operational briefings. In every dimension, technical, tactical, psychological, the Thunderbolt had reshaped the Luftwaffe's perception of air combat. In retrospect, the significance of the captured Thunderbolt extends beyond its immediate operational impact. It exemplifies the intersection of industrial philosophy, engineering design, and tactical adaptation in a high-stakes conflict. German personnel recognized the aircraft's advantages not merely as mechanical attributes, but as manifestations of a systemic approach to warfare, integrating material abundance, redundancy, and sustained combat effectiveness. The psychological consequences were profound. Pilots confronted the limits of individual skill when faced with an adversary whose resilience could absorb conventional tactics. Engineers faced the reality that understanding a design was distinct from the ability to replicate it under wartime constraints. By the autumn of 1944, Rechlin's evaluation program concluded, and the P-47 was retired from active testing. Yet, its legacy endured. Subsequent German aircraft designs incorporated select lessons in survivability and redundancy, though never to the extent achieved by the Americans. Pilots who had flown the captured aircraft recounted the experience in memoirs and reports, emphasizing the psychological shift induced by direct observation and engagement. Even decades later, historians and aviation experts cited the Rechlin evaluations as a pivotal example of how industrial philosophy could decisively influence operational reality in modern warfare. The Thunderbolt had taught an enduring lesson. Technological and tactical skill could only achieve so much when confronted with systemic industrial advantage. Germany could study, document, and emulate aspects of American design, but the underlying strategic disparity rooted in material abundance, production capacity, and integrated engineering philosophy remained insurmountable. The aircraft's 8 50-caliber machine guns, its reinforced fuselage, and its resilient control systems were not merely technical features, they were expressions of a broader principle. Sustained operational effectiveness derives from foresight, resources, and redundancy, not solely from agility or pilot acumen. For those who had witnessed the evaluations firsthand, the captured Thunderbolt became more than a machine. It was a teacher, a benchmark, and a mirror reflecting both the strengths and limitations of the Luftwaffe. Pilots and engineers internalized lessons that would influence tactics, training, and design discussions for the remainder of the war. They understood that the aircraft's resilience and firepower imposed constraints on engagement strategies, shaped psychological expectations, and underscored the broader implications of industrial disparity. In essence, the Thunderbolt's legacy was both practical and philosophical, bridging the gap between empirical observation and strategic insight. As the first snow of December 1944 fell over Rechlin, covering the airfield in a blanket of frost, the Thunderbolt stood silently, a testament to a design philosophy that prioritized survival, endurance, and lethal efficiency. Its influence permeated the Luftwaffe, challenging assumptions, altering tactical doctrines, and reshaping the psychological landscape of those who had studied it. The aircraft had endured the scrutiny of enemy eyes, the test of repeated evaluations, and the judgment of experienced aces. In every respect, it had validated the principles of American industrial and engineering philosophy, demonstrating that in modern warfare, resilience and redundancy could be as decisive as skill and speed. The captured P-47, while never deployed operationally under German control, achieved a form of immortality through its impact on thought, perception, and doctrine. Pilots, engineers, and commanders alike recognized that while combat skill and tactical ingenuity remained essential, they were insufficient when faced with an adversary whose machines embodied a philosophy of endurance, redundancy, and overwhelming firepower. In this recognition lay the enduring lesson. The balance of power in war is shaped as much by industrial and engineering foresight as by the heroism or skill of individuals. The aftermath of the captured and tested P-47 seconds lingered like a silent verdict over the Luftwaffe's offices and flight schools. By the winter of 1943, the reality of American air power was no longer rumor. It had been quantified, documented, and dissected. Test pilots who had once prided themselves on their mastery of German aircraft now carried logs detailing how a single-engine fighter, nearly twice the weight of a Messerschmitt Bf 109, could absorb punishment that would have destroyed any Luftwaffe plane. These evaluations reached technical bureaus in Berlin, pilots' training regiments, and the Reich Air Ministry itself, subtly reshaping expectations of survivability, armament efficiency, and operational resilience. At Rechlin, the Circus Rosarius staff continued experimentation. Major Hans Werner Lerner, who had flown over 200 combat sorties on the Eastern Front, evaluated the Thunderbolt under sustained fire. Ground crews fired 20mm cannons while 8 50-caliber rounds simulated counterstrike. Even after direct hits to fuselage, engine, and wing routes, the P-47 maintained structural integrity. Minor deformation occurred, but flight control remained. This was not marginal survivability, it was a paradigm shift in armored fighter design. German engineers realized that Republic aviation had prioritized power and redundancy over agility. The Pratt & Whitney R 2800 double wasp engine generated nearly 2,000 horsepower, later enhanced to over 2,500. Armor plating, self-sealing fuel tanks, and backup systems rendered conventional ordnance less effective. The Thunderbolt disrupted Luftwaffe tactical doctrine. German pilots trained in turning dogfights found that the P-47's operational envelope defied expectations. In dives from 20,000 feet, the aircraft accelerated beyond safe velocity limits for German planes, yet maintained control. German pilots could inflict damage, but the target's durability and counterfire made conventional engagement increasingly untenable. Intelligence officers quantified the disparity. By the end of 1943, American factories had delivered thousands of P-47 seconds, whereas German production struggled under material shortages, bombing, and labor allocation. Any tactical innovation would be limited without addressing the overwhelming American industrial base. Training regimens evolved. Units incorporated intelligence from captured P-47 seconds, emphasizing caution in frontal engagements and avoidance of extended dogfights at high altitude. Pilots were briefed on strengths: armored cockpit, resilient fuel systems, high-speed diving, and 8 50-caliber guns that often outperformed German 20mm cannons. Psychological conditioning encouraged recognition that superior firepower combined with resilience was a design choice, not luck, aiming to reduce panic in combat. German engineers faced material constraints: aluminum alloys, welding, lubrication systems, and turbocharger placement in American aircraft optimized long-term operational stress. Attempts to retrofit Bf 109 seconds or FU 190 seconds with additional armor or redundant systems were unsuccessful, compromising maneuverability and engine performance. The lesson was clear. Industrial philosophy, how a nation produces and sustains machines, was as decisive as isolated technical innovations. Operational reports reinforced this. Escort missions over the Ruhr Valley in early 1944 revealed formations of P-47s, absorbing multiple hits, yet maintaining combat capability. Minor fuselage damage and superficial perforations failed to compromise engine function. In contrast, Luftwaffe losses were disproportionately higher. Post-mission analysis highlighted a consistent pattern. Durability, firepower, and high-altitude performance produced an asymmetric advantage. It was the synergy of engineering and tactics, not pilot skill alone, that dictated outcomes. The psychological effect on German pilots was profound. Journals and memoirs reflected awe and respect, describing the P-47 as a fortress in the sky or a rolling tank. Training and engagement strategies shifted. Units avoided head-on confrontations, prioritized altitude control, and coordinated attacks to exploit theoretical vulnerabilities. Commanders recognized that even if some P-47s could be destroyed, the sheer volume of American production and aircraft resilience made attritional strategies ineffective. Strategic planning shifted toward interception, night operations, and complementary anti-aircraft artillery. By spring 1944, the impact of captured P-47 evaluations crystallized into doctrine. Pilot training incorporated lessons on aircraft resilience, engineering bureaus documented material constraints, and planners acknowledged the limits of attrition. The Thunderbolt had achieved more than battlefield victories. It had rewritten the mental model of what a single-engine fighter could accomplish when backed by industrial might, meticulous engineering, and tactical foresight. The captured P-47s demonstrated a fundamental principle of modern warfare. Technological superiority, integrated with production capacity and strategic deployment, could decisively shift combat effectiveness. German engineers, pilots, and commanders confronted realities that challenged assumptions, doctrines, and psychological comfort. The Thunderbolt's endurance against 20mm cannons and its counterfire with 8 50-caliber guns were emblematic of American engineering philosophy, operational pragmatism, and industrial foresight. These aircraft were not merely objects of study, they were teachers, reshaping Luftwaffe, understanding of aerial combat, survivability, and how material advantage could influence a global conflict. Even as Luftwaffe pilots continued to fight, the lessons lingered. Tactical adjustments, cautious engagement strategies, and enhanced reconnaissance could mitigate some disadvantages, but the overarching truth was undeniable. The P-47 represented a combination of resilience and firepower that German doctrine could not match. Each mission against it reinforced the lesson that engineering philosophy, not just pilot skill, defined the trajectory of the war in the air. The captured Thunderbolts became symbols of an industrial and technological superiority that the Luftwaffe could neither replicate nor ignore, leaving a lasting impact on the conduct of air warfare and the strategic calculations of both sides. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.